So let's finish out chapter 9 with real gases and about the last 10 slides of this lecture series. So up until now, we've been talking about ideal gases. So we've thought as of gases as just these minuscule ping pong balls with no volume and completely elastic collisions and no interactions with one another or the container. You just think of them as just perfect ping pong balls with no volume. Okay, so real gases do not behave this way. We were able to consider ideal gases ideal at Earth-like conditions, so that means low pressure and high temperature. But uh, we have to consider the implications of real gases and how they deviate from ideal gases at high pressure and or low temperatures. So at either high pressure or low temperature, there are some assumptions of the kinetic molecular theory that we looked at in the other slides that aren't valid. So let's look at two of those postulates. So if we're at high pressure, that means that there is a lot of molecules in a space, in a volume. So postulate 2 goes out the window because there are so many molecules. So real gases have molecules that occupy some volume. All right. So at high pressure, that postulate isn't valid anymore because there's so many molecules now at high pressure that we have to actually consider the volume of the molecules themselves once that concentration is so high. And then finally, at low temperature, you can think, at low temperature, there's not a lot of kinetic energy for those gas particles to be moving. So if they're not moving very fast, if they're moving slow enough to one another and they collide, if they're slow enough, the attractions that those electrons, provide in a molecular structure may be important when molecules are moving very slowly. And so here, our third postulate, gases may attract one another to some extent. And that is really important at low temperature. And so the first one was important at high pressure. So that's how you kind of have to think about it. All right. So here is a graph kind of showcasing that. So we essentially have pressure on our x-axis and then PV over nRT. So essentially this is like our moles, essentially. So what this graph is showing, the straight line, if you had a perfectly ideal gas, that ideal gas, like if you just had a container of ping pong balls that were had no volume, but they had mass and they were gas particles, it would follow this straight line at all pressures. It would still maintain a mole, like the number of moles of being 1. The only time that these real gases actually follow the ideal gas line is right here at this point. So at very, very low pressures, all of these gases fall on the ideal gas line. They all start here, so at low pressures. So, on this graph, 200 atm is right here. So 1 atm, like, where the pressure on Earth would be somewhere like really close to the 0 line. So at 1 atm, at low pressures, all of these gases follow the ideal gas line well. Where the real gases don't behave ideally or any increased volume. So all of these other volumes that don't fall on this line, or sorry, all these different gas examples that don't fall on this line are considered real gases, and we need to consider essentially these two things, the actual volume and the actual attraction between molecules at high pressure. So that's when we vary pressure. Let's also look at different temperatures. So here's the same graph, type of axis where we have pressure and then PV over RT on the y-axis. So for moles to keep the same number of moles, our ideal gas will be on this straight line here. So you can see we have 3 different lines showcasing how this graph changes for nitrogen gas at different temperatures. So here, in order to have an ideal gas, we need this line to be the line for the substance to be pretty straight and horizontal. So we see at 200 Kelvin, so pretty cold, like that's like negative 173 Celsius, that's pretty cold. You see that we have a very, very curved line that does not follow the ideal gas line at all. If we increase the temperature to 500 degrees, So pretty hot. That's like over 100 degrees Celsius. That we see the line. It's still curved, but it's starting to flatten out. And then at 1,000 degrees Kelvin, which is pretty dang hot, the line starts to flatten out, and it's approaching a more ideal type of picture. All right. So this kind of proves that at high temperatures, gases behave more ideally. Not quite ideally, but it is quite ideal. But so particularly at low pressures and high temperatures. So this part of the graph right here, low pressure, high temperature, we have a fairly um, ideal gas because it lies right on that line. So what was I going to say over here? High temperature gases behave more ideally, right? And then over here, where we say at low pressure, um, gases behave more ideally. Okay, so how can we change our uh, ideal gas law to now consider real gases instead of just ideal gases? So thankfully, we don't have to learn a new equation. We're just going to add some little adjustments to our our regular ideal gas law Pivnert equation. So, in order to account for real gases, so again, this means at either high pressure or low temperature, is when we have to kind of consider real substances as real gases. We're going to use the van der Waals equation. All right, so that's what this equation is, but I'm going to show you that it's actually just the ideal gas law with a skirt on, essentially. So the van der Waals equation models the behavior of a real gas. This equation is just the ideal gas law equation, just with two extra things. And those two extra things are this A term and a B term, which are constants that are specific to the sample. So specific to the sample or substance. So if you have like CO2, you would look up A and B values for CO2. If you had nitrogen gas, you would look up A and B values for nitrogen gas. So specific to sample. All right. Okay. So what you see here is you have P plus N squared, which remember this N is the same N as our N in nRT. So N is just moles, the number of moles of our sample. N squared times A, that's our constant that you just look up. And then over volume squared. So you kind of have to know the number of moles and the volume of your container. All right. So this term is just, you can just think of this whole term. I don't know what color I want to use. This whole term is our old, just like P ideal portion of the equation. But now we've added this little amendment to turn the ideal gas law into the van der Waals equation in order to account for real gases. So that's the P term. So PV equals nRT. So now the V term also has something that is adjusted. So you see the V term, which is here, is now V minus N. So this is the same, N moles that we were talking about, times the B constant that we just look up. So these are constants that you just look up. They're literature values. All right. And then equals nRT. So that part of the equation stays the same. So essentially what we have here is this, we have this component that adds itself to the pressure. And then we have this volume term that subtracts from volume. So I'll show you how A is related to our pressure term and how B is related to our volume term. So if we take a deeper look into A and B, these constants that you just look up. So a large A value here in the van der Waals equation means that there's a stronger intermolecular attraction between gas molecules. So if there's a strong attraction to the molecules to one another, then essentially a lot of the kinetic energy that would just go into collisions is now going into breaking intermolecular attractions. So if all of your ping pong balls now are hugging each other, you're going to measure a smaller pressure than what you typically would, because now instead of bouncing against the container, those molecules are now sticking together a little bit more closely than they normally would. So that's why we have this, we have this addition term of A, because you can think of this whole term as our old P ideal value. And so this term, or this P that's actually in the van der Waals equation, this is our P measured. This is what we actually measure. So our ideal pressure will be larger than our measured pressure. And that's because with stronger intermolecular attractions, some of that pressure is being taken away. All right, so that explains A. A larger B corresponds to larger molecules overall. So B also, this B term that is attached to our volume term, it also, see how it also depends on the number of molecules. So you can have a really large B, but if you only have like a handful of molecules in a sample, the large molecules aren't going to really make a big difference to the volume. But if you have a lot of molecules, a lot of moles of gas in a sample, you can see how together with the B constant, you can start to take away, you can start to take away some of the volume used in this calculation. So a larger B value means that the molecules themselves are larger. So essentially you're subtracting, making the volume smaller than it actually is ideally. So, I can call this whole term our ideal volume, and then this would be the actual like measured volume that you measure when you take account of the moles of the actual volume of the particles. So usually when we see A and B in the van der Waals equation, they increase together. That has to do with dispersion, London dispersion forces, which we'll learn about in chapter 10, the next chapter. But typically you see them increase together, but not always. All right. So here are some van der Waals constants for different gases that you might see. So just remember A has to do with attractions. So if you see dipoles, usually attractions, I don't know if that's spelled right. So dipole, if you see any permanent dipoles in the molecule, then you're probably going to have a pretty large A value. So look for dipoles or molecular dipoles. Meaning if the molecule is overall polar, then it's probably going to have a large A value. And then we'll look through these. And then B is size, volume. So just use molecular weight as an indication of the magnitude of our B value. If you need to compare to different substances and you have to think about the B value, use the molecular weight. All right, so here we have a bunch of different gases. So like I said, when you're looking at attractions to see predict large A values, look for those molecules that are polar. So I'm looking through this list. Okay, none of them are polar except water. I know water is polar. And so let's look at its A value. Oh yeah, A definitely does have a pretty large A value compared to these other ones. All right, but then, wow, this CCl4 also has a very large A value. So that might be due to the polar bonds, the natures of the polar bonds between chlorine and carbon. Oop, are you showing up? Okay. Chlorine and carbon, that's a very polar covalent bond. And then all these nonpolar molecules like diatomic nitrogen, oxygen, and helium. Wow, helium has a very, very small A value. Because it is the smallest atom within this whole group. It just has 2 protons and 2 electrons there, so there's very little in terms of attractions when bouncing against the walls. But then you also see here CO2 also has a relatively large A value, and that's because there are dipoles in the molecule, but there is no net dipole, so it is lower than water because there's no net dipole. Those 2 dipoles cancel one another out. All right, so let's also look at the B value. B value will take care of the volume correction for the for the van der Waals equation. So essentially, let's just look at the molecular weight of these things, and that will give us an indication of the magnitude of our B values. So oxygen and nitrogen gas, they have pretty similar molecular weights. I can write them down here. I think our molecular weights are about 20, I think 28. Oxygen is 32. CO2 would be 32 plus 12, 44. Water is 18. Helium is 4. And CCl4 is a lot. It's like 70 plus 70, 140 plus 12. So it's like about 150. I'm just going to guess. So it's really heavy. So using those molecular weights, we can kind of see the trend that those B values make. So the B values for nitrogen and oxygen, they're similar. I mean, it kind of goes against the opposite of the trend that we see. Usually the trend is the larger the molecular weight, the bigger the B value should be. But here, like, let's see CO2. CO2 is like definitely larger than either oxygen and nitrogen. And you can see that its B value is larger than both of those. The difference in molecular weight between nitrogen and oxygen just isn't enough to see a real difference in a B value. But then, so we look at water here. Water and helium are our lightest gases in this set, and you see that they do have the smallest B values. And then our CCl4 has the largest molecular weight of all of them, and it also has the largest B value. So these examples clearly showcase the different trends we see with A and B values. All right. So let's take a deeper look at those two correction factors that we made to the ideal gas law to come up with the van der Waals equation. So remember the two constraints for an ideal gas, it's low pressure and high temperature. So we have to consider things to be a real gas at high pressure. All right, so this is where one of our terms comes into play. So at high temperature, our postulate number 2 breaks down. Postulate 2 says that gases are mostly empty space. But at high pressure, molecules are no longer separated as much. There's not as much space between molecules at very high temperature because there's so many molecules in just like one small area. So we can no longer assume that the volume of the molecules themselves are negligible. That was our, postulate number 2. Compared to the volume of the container. So in a real gas, those molecules actually do occupy some space. So here is an example. I have a container with some gas particles in it. All right, let's call this low pressure. So if we want to increase the pressure of the system, all we have to do is decrease the volume. So if you take your piston and start to make the volume smaller and smaller and smaller, now you have a higher pressure. And you see that there's less free space between all of the molecules. So you can think, okay, now the molecules actually come up with a good percentage. The volume of the molecules themselves are actually a good amount of the volume of the whole container itself in this high pressure scenario, because there's not as much space between those molecules. So the volume in which the molecules are free to move is less than the whole volume of the container, right? Because like this molecule, it can't occupy every single space in this container because other molecules occupy that space. So this is where our B value, our constant, comes in. So our ideal volume is actually equal to the volume of the container minus the number of moles of your sample in that container times our B constant, which is essentially the effective volume of 1 mole of gas particles. If I took all of those gas particles and crammed them all together and got rid of all of the space, right, that volume that sample takes up would be our B value. And I believe that our B value has the unit of liters. I'm pretty sure it's liters per mole. Let's just take a look. Yep, see, our B value is liters per mole because we're multiplying it by, too far, but by that N value. All right, so at high pressures, molecules are so packed together that their volume actually matters. That's how we go from an ideal gas to a real gas at high pressures. All right. So our second constraint was low temperatures, so we have to consider gases to be real at low temperatures. So this kind of goes against postulate number 3 of kinetic molecular theory, where it said that all molecules don't have any attractions to one another. You can just think of them as like these ping pong balls with completely elastic collisions. So at low temperatures, now the attractive forces between molecules are no longer zero. So when you cool down the system, like I said before, kinetic energy will decrease. All right. So if kinetic energy, so temperature goes down, kinetic energy goes down. So then our velocity, or our RMS speed also goes down. Things are moving slower. If they're moving slower as they move slow past one another, they're next to each other long enough to feel some type of attraction before they go off. And that attraction does change some things, and it changes pressure of the container actually. So what am I saying here? So they begin to feel the intermolecular attractions. We will go into more detail about intermolecular forces next chapter. I just want you to know how to use the van der Waals equation. Right, so at low temperature, the molecules will now attract to one another and make fewer collisions than they would ideally. Right, so what happens, since they're making fewer collisions with the container, we'll observe a lower pressure than expected from ideal. So here's a nice picture that kind of showcases this. In an ideal gas, there's no intermolecular attractions to one another, so everything's just ping-ponging against one another and the walls of the container. But now, with a real gas, the molecules feel some type of attraction towards one another, so it'll be making less collisions with the outside of the container, so our pressure that we actually measure will be lower than typical. These should be subscripted, but it's not. So that's why this whole term is in the van der Waals equation. So same thing with our volume term. Whoops. This whole thing is in our equation. Okay. So our constant that we use is our A value that takes into account intermolecular forces. Again, we will bring up intermolecular forces in chapter 10. And so we're multiplying this A value by an mole over volume squared, the whole thing squared. And essentially this is just a concentration terms, right? Moles per volume is just concentration. And because attractions happen between two molecules, we square the concentration. So it's just the concentration term that corrects corrects for intermolecular attractions when put together with our A value. All right, so if we substitute both our P ideal and V ideal into our ideal gas law, or ideal gas equation, remember P, so it'd be P ideal times V ideal equals nRT. Right, so just substitute these two terms in for what we just discussed, and now you get the van der Waals equation. So now you clearly see that this equation is just the ideal gas law with a skirt on. All right, so calculations work very similarly to the ideal gas law equation. It's just a little bit more work because you need to know the A and the B value. So you kind of have to know what molecule, what system you're working with. And so again, usually in a question, I will say like, hey, consider this system a real gas system. Most of the time you can get away with just using the ideal gas law, and that's at at low pressures and high temperatures. So like if you have gas samples on Earth, right, and we're just talking about like balloons and things that like you and I can get our hands on. But if we're talking about like different scenarios, like really expensive, like high pressure machinery or really low temperature, devices, things like that, we can't use the ideal gas law. But again, I will tell you when to use what type of equation. Okay, so let's do a problem and finish out this chapter. So calculate the pressure exerted by 1 mole of CO2 in a 2-liter tank at 298 Kelvin. First, let's do it using the ideal, according to ideal behavior. So consider the substance, the sample, an ideal gas. And then the second one, non-ideal behavior. So we're assuming ideal gas for this first question. And so we're going to use just our regular PV equals nRT. And what are we calculating? We're calculating the pressure. All right. Okay. So that's easy enough. So P equals nRT over V. So let's just plug stuff in. So we have a mole of CO2, cool, 1 mole, times R. Make sure you use the right R, because now we know 2 different types of R. We're back to ideal gas law stuff. So 0.08206 liter ATM mole Kelvin times temperature, what is it, 298? Great, they did it for us. Over volume, what is that, 2.00. Our answer should have 3 sig figs. So plug that into your calculator. You get, this is 12.2 ATM. So this is our ideal pressure. So if we just assume all of those CO2 molecules, they don't have any attractions to one another, they aren't, they're mostly empty space, that they take up negligible volume in the container, then the pressure would read 12.2 ATM. All right, so the question also says to do non-ideal behavior. So we want to treat it as a real gas. So use the van der Waals equation. And look, they give us our A values. So our A value is here and our B value is here. Great. And I think we're calculating for pressure again. So let's just write out the whole equation. So P plus n squared over V squared A, that's our first term, V minus NB equals nRT. So we want to solve for pressure. We know everything else. We know the number of moles of the system. They gave it to us. We know A, we know volume, we know everything. So we can just put everything in and solve for pressure. So let's just move some stuff around so it's easier. So pressure plus n squared A over V squared equals nRT over V minus NB. I'll just move this over here and make that minus. All right, can I do that? Yeah, I can do that. Okay, so there's our equation to get our pressure. So let's just plug stuff in. At this point, it's just plug and chug. We know all the values. So 1 mole. I'm just going to drop sig figs at this point. It'll come out to 3 sig figs. 1 mole. R is 0.08206 liter ATM. Mole Kelvin. Temperature 298 Kelvin over volume. I think it was 2 liters. Yeah, 2 liters minus NB. So N is 1 mole. And our B value, which is up here, is 0.0427 liters per mole. So essentially what that value is saying is that a mole of CO2 molecules will take up this many liters. So this is what? This is about 42 milliliters. If I have a mole of CO2 molecules and I cram them all together, it will take up this much volume. So you see, it takes up 42 milliliters of 2 liters. That's how it's changing that volume. Okay, so there's that first term. Do I have to give myself more room? No, I think I'm okay. Minus n squared, so 1 mole squared times our A value. So 3.59 liters squared ATM mole squared. And then on the bottom is 2 liters squared. And cool. Let's just take a look at units. So moles cancel. So moles cancel here, and then you see that we're left with liters, all right, on the bottom there. And then liters will cancel there, all right. And then what else? Temperature cancels. So it looks like we're just left with ATM here in this term. And so if we look over here, mole squared cancels, liter squared cancels, and we're also left with ATM. So ATM minus ATM. So our answer will be a pressure. Great. And so if you stick this into your calculator, you should get a pressure, a measured pressure of 11.6 ATM. Great. So if you actually consider attractions of the molecules and the volume of the molecules themselves, you will get, for CO2 in this particular system, you'll get a pressure of about 11.6 versus the 12.2 atm if we consider it ideally. So this is about a difference of 5%. All right, so it's not that different. Like going with the ideal gas law, it'll get you pretty close, but it's not anything that we can also ignore. We can't just ignore these things. All right. Okay, so that's how you do that question. It's very much the same as just a straightforward ideal gas law equation. You just have to add an A term and a B term. Okay, so let's do one last problem. I like conceptual problems. I think it tests your ability past just being able to plug stuff into your calculator. So this question will really gauge you on if you know how to interpret the van der Waals equation. So this problem has no calculation. So you have two separate identical containers at the same temperature. One container contains 1 mole of nitrogen gas and the other one a mole of carbon monoxide gas. Both molecules are the same size. They actually have, I think they have the same molecular weight. Yeah, they both have a molecular weight of 28. Molecular weight equals 28 grams per mole for both. If we consider N2 and CO as real gases, which container would you predict to have the higher measured pressure? So I didn't give you any numbers here except the number of moles of gas. That's it. All right, so we just have, I don't know, we have my balloons. They have the same volume. One balloon contains nitrogen. The other one contains CO. Which one has the higher pressure? So let's just remember our van der Waals. P minus N, oh wait, no, plus N A. Actually, I don't even think you really need to look at the van der Waals equation, but we can anyway. So remember what the van der Waals equation says, that we have to adjust for attractive forces and we have to adjust for volume of the molecules. The question says that both molecules are relatively the same size. The molecular weights are both 28 for both of them. So I'm going to predict that B will be the same. B will be the same for N2 and CO. So that doesn't help me that much. And anyway, B just changes the volume. So it doesn't directly change the pressure. All right, so let's look at the other factor that contributes to the van der Waals equation. That's the A term, or the attractive forces. So are there any attractive forces in diatomic nitrogen? Well, if we draw out the Lewis structure, you see that nitrogen has these lone pairs, has a triple bond, but overall diatomic nitrogen is nonpolar. While CO, if you draw out the Lewis structure, it has a triple bond and 2 lone pairs as well, but it has an overall dipole. So I would predict CO would have the larger A value. So if CO has a large A value, or if you think of it this way, CO, carbon monoxide, has intermolecular forces present. There's attractions. Has a larger A value, so it has attractions between molecules. So there will be less collisions against the container. So therefore, the measured pressure will be less collisions against container. So pressure will be less than measured. And so that's what the answer is here. What was the actual question? It says, which container will have the higher pressure? So yeah, the answer is diatomic nitrogen because it's nonpolar and has no attractions or a small A value. Versus CO has a larger A value. There are attractions between molecules. And so since the molecules are attracted to one another, there are less collisions overall against the container, so your pressure will be less. So this is a nice no calculation, can you interpret van der Waals equation type of question. So that wraps up chapter 9. When we get next chapter 10, we will go over extensively intermolecular forces, which are very important for the rest of your chemistry career and especially 1220.